Yeah, we may start now.
Okay, ma'am. So, thank you so much, ma'am, for giving this opportunity. But I'm very sorry for this delay. Reason is that parallelly we are
No
conducting some
problem.
seminars, and even I came for a doctor appointment, and I just came. So I'm very sorry for that. So today I'm going to talk about the uh, burst super resolution topic. The actually title of the today's lecture is Gated Multi-Resolution Transfer Network for Burst Restoration Enhancement. So it's a very latest kind of restoration problem for using burst. So in my topic, I will be in my this lecture, I will be covering like what actually the traditional super resolution and what actually the people are doing currently. So what are the new trends in this? Even my topic of lecture is also recent trends in deep learning. So I will be talking on burst super resolution or restoration. So this work got accepted and published in CBPR 2023. So actually this is a joint work, a student, a PhD student from our laboratory. And then similarly, we have a collaborator from so ANU, and then Inception Institute of Artificial Intelligence, Abu Dhabi. So let me start this actual content. So what is the motivation for using burst super resolution and burst restoration? So if you guys already know super resolution, what actually the super resolution, if I am having a image size of um, let's say 100 by 100, so I want to convert that to the 200 by 200. So with more detailed information, it should be generated. Like there are image resizing options are there, either in maybe in the MATLAB or maybe Python, by using image resize command. So there it is using the traditional interpolation algorithms like bilinear interpolation, bicubic interpolation, or nearest neighbor interpolation. So these three types of interpolations are generally used for the uplifting the image. So the main definition of converting image from 100 by 100 to 200 by 200 is nothing but you are interpolating the pixels in between. Like for each pixel, you are going to interpolate another pixel. Like here I'm having 100 pixels with 100 by 100, means 100 rows and 100 columns are with me. So I'm interpolating 100 again, that many. So means alternate rows again will be interpolated, alternate columns will be interpolated, so that 4x size number of pixels, let's say here in this case it will be 10K, but here it will be, so now it will be 40K. So it's actually the 4 times. So this is the main problem of interpolation or upscaling the image. So for this traditional image super resolution concepts are like this way. Let's see, if you take any photograph, this photograph will be applying, it is collected from the sensor, and then we will apply the super resolution on this. So we are getting the whatever the image with the super resolution, we are getting the high resolution image we are generating from here. Okay. So but if we see this now, in this case we are actually losing some information. So if I'm playing again, in this case, whatever the fine details are there, these fine details are missing. See here, this information is actually missing. So but I'm able to improve the quality as compared to this, but so still there are lots of useful information that needs to be addressed. So at this point only super resolution has burst super resolution has come into the picture. That is already available in these days, like in iPhone live photographs you can use, like where it is collecting small number of video frames. It's a small video it is collecting. So from a group of these video frames, we are going to restore the image, which will be having high resolution, so that we are able to get the, even you can see these fine details are able to restore when we go with the burst super resolution. So I guess you understand that what exactly the case. If I am collecting a same scene, instead of collecting single photograph here, I am collecting one photograph here and bit shifting photograph, and another shifting like maybe horizontally and vertically, like few number of images I will collect for the same. So those images are utilized as an input to the your deep learning algorithm, and then from there you are going to restore it. So the main motivation for this is that when we are collecting a photograph with even with 2 microseconds duration, like 30 frames per second, or even it 400 frames per second if you collect. So if you take the 2 consecutive frames, so there will be a variations in the intensities. So reason is that there is an illumination variations. Fine means very fine level details. If you observe, then only you can observe. So you can able to understand that there is an illumination variations. Because of that, any 2 consecutive frames, if you consider, so those are not exactly same. There will be variations in that, in terms of maybe, because if it is a video and there is a motion present in that video, in object's motion, so definitely these are getting means these edges because of this motion. So these, because of these edges, because of this motion, we can able to see the edges and other kind of information. So let's say if I'm playing a video here. I think, yeah, we are able to play here. Let's see here in this video, we are collecting all these frames, and with these frames, we are able to convert that into the another image. That is a high resolution image from this. So this is the main motivation. Let's say if I am collecting a photograph at t seconds at one location, let's say this location. So another one like this circle one, like whatever the indications are there. And if I am collecting same with another t plus one's location, so if you see the maybe tth location, maybe there is a loss of information at that particular indicate that signboard, but at t plus one there may be a information in that. So if we utilize a deep learning algorithm and mixing those 2-3 images which are collected with different spatial locations, so that you are able to get the high resolution image. So this is the main motivation of developing a high resolution image generation or burst super resolution. So here also we can able to remove the noise. There may be a kind of noise, that noise needs to be removed. At the same time, here if you see these are all images are collected with different distances, and means there is a misalignment in the objects. If you see the 2 consecutive frames, even if I am picking this one, if I am trying to pick this what is this sign, I am not able to pick, because there is a large variation in that. There is a misalignment in the object locations in 2 consecutive frames that needs to be addressed. And then we are taking the raw frames. Using all these frames, we are converting this data to a single high resolution image. Okay, so the flow diagram, if I show you, so I will be collecting so many frames. Actually, in my experimentation, we have considered 14 frames. So 14 frames are collected, and using these 14 frames of short video, we are processing it using deep learning algorithms. Like again here, encoder decoder kind of architecture only used here. So as I said, we need to work out for noise removal, because when we collect with different illuminations, noise is an issue. And another one is misalignment of the object's locations. So that is the reason we have to work out for this burst super resolution with the different modules. Like one module is alignment module. One module is alignment module. After alignment, we need to go for the feature merging or feature extraction for the better restoration. And after that, the requirement is that, let's say this is 100 by 100. But you need a size of maybe 2x size, which is nothing but 200 by 200. So upsampling is also required. That's why third module is an upsampler. So this is the final resultant response for a given burst of 100 by 100 size with the number of frames, maybe 14 channels here, 14 not channels, 14 frames here. So with that, you are getting a 200 by 200 color image. So this is the main flow diagram for the burst super resolution. So let me talk one by one modules here. First one is a burst feature alignment module. So burst feature alignment module itself is a challenging task, because feature alignment, which is actually initially we used to work like using traditional algorithms for image registration. So image registration means you are having two images, and these two images you need to identify the locations which are actually same. So based on that, you are able to align that. So even for image stitching point of view also, you need to identify the common region, and then you can able to stitch that. And image fusion case, if you want to fuse two images, again I need to identify. So this is mostly image alignment or data alignment is a very much essential task for the when you are comparing two images. So it is a very challenging task when there is a misalignment between two consecutive frames in the burst video. So that's why what we are taking here, even if you see the iPhone, it will ask the which image you want to consider as a reference frame. So generally it consider as it takes in iPhone, it collects 9 photographs in single burst. So center one consider as a reference, and then right side 4 and left side 4, total 9 frames are there in a small burst. So center one is considering as a reference frame. And technically, if I speak here, if normally if I speak here, so reference frame, from reference frame, I am collecting the 4 frames left side and 4 frames right side. But reference frame is not, this is not at t equal to 0. Ideally, this is not a causal system, because at a t equal to 0, how can I collect the future 3 frames? I cannot collect the future 3 frames. Like if I am asking, if I am talking right now, I cannot say what will be this image after 4 seconds, because the future information is not with me. But I can talk about what about the information for last 10 seconds also. Ideally, when I click my photograph, it is taking at this location only. So from this location, it is picking 9 frames, but I am collecting center frame as a reference frame, because I would say that center frame is less likely misaligned with the other frames. If I consider this one as a reference frame, what happens? This frame is mostly it's largely misaligned with this frame. So and it relatively less it is coming. So but if I consider again, if I consider this one, this is a misalignment. But if I consider this one, again this is a misalignment one. But if I consider this one, so it will be again misalignment. If I take this one optimally, I can able to select this one as a reference frame, so that I am able to get the less distortions in my restoration. That is the reason iPhone is considering center frame as a reference frame, and based on that, it is going for the restoration, high resolution image restoration. If you observe, if you guys are having iPhone, open it and open any image or you collect any photograph, and if you display that once, it takes few maybe very microsecond duration, but you can able to observe that those edges are become boosted. So this edge boosting you can able to see, and resolution improvement you can able to see, but it is happening in the few fraction of seconds. So but you can able to observe it. That is the main technology of this burst super resolution. Similarly, Samsung phone also started this kind of burst super resolution. So now coming to the execution part. So even in my paper, we have proposed a multi-scale burst feature alignment module. So because we are going for multi-scale, so multi-scale feature alignment or multi-scale feature extraction is well known in literature, and it is actually showing the better performance as compared to single scale. So multi-scale generally happens either changing, either getting the two means different filter sizes, one possibility, and or other one is like change the image size. One possibility is that if I am taking 100 by 100 image, so on that I will work out, and after that I will decrease it to the 50 by 50. On that I will perform, and then 25 by 25, and so on. Like that I will be getting multi-scales. That is one possible one. Other one is like I may using 100 by 100 image only, but my filters are 3 by 3, or maybe 5 by 5, or maybe 7 by 7, and so on. Or maybe one, I will start with 1 by 1, 3 by 3, 5 by 5, 7 by 7, and so on. With that, I'm able to get the multi-scale information. So I'm assuming you guys all you know all this information. That's that way I'm teaching here. If you are having any problem, I think regarding multi-scale, I think you have to read some deep learning concepts. How this multi-scale concept, even it is not only in deep learning, traditional feature extraction algorithms are utilized in multi-scale, multi-square filter banks. It's maybe wavelet is also multi-scale or multi-resolution analysis. Same manner, it is here. So I'm considering the reference frame. So in iPhone, it is a middle frame. And then current frame means I'm starting this feature extraction part for misalignment. So alignment purpose, whatever the misalignment, I will be aligning it. So first frame, frame number 1, and let's say this is a frame number 5. So with this current frame is a frame number 1, and then when I process it for next frame, it will be frame number 2, but this reference frame is a frame number 5 only for this entire burst. So using that, I am concatenating these two, and then after concatenation, what I am doing, I am sending a MKGA, which is nothing but multi-scale gated attention module. So multi-scale gated attention module, what it is like, I am using a one layer normalization, followed by I am using 3 different scales, 1 by 1, 3 by 3, and 5 by 7, 5 by 5. And after that, whatever it is game, again I perform the layer normalization. After that, I am giving it to the one transformer block. So what is called transformer, I will be explaining in later slides. But here in transformer block, we are having a query, key, and value. Value is a kind of data feeding. It means a similar kind of like simply applying a small convolution, which is nothing but small adjustment or maybe kind of mutation kind of operation you are performing on the given data. But query and the key are generating the attention mechanism from there. It is actually generating the attention. So query actually works for the what type of task it is. So keys means key says that what type of task you need to make, and query performs the that kind of required task. Based on that, I will be getting the attention mechanism. So that attention will be multiplied with the again value. That is value is nothing but as it is content applied with a small convolution. It means it is carrying more information as it is information of the output, means given input. But query and key is generating the attention. Based on that, I will be getting the output. That is here I am saying R, which is nothing but attention multiplied with the input feature maps, which is nothing but where actual information is there, it will be giving more importance, and where unwanted information is there, it will be giving less importance. Like that, I will be giving one block here, And after that, I will be performing one downsampling operation. Similar procedure is performing for two again downsampling operations. So here, once I perform this operation, I will be taking gain reference and current frame, and these features both are concatenated. And after this, I am performing some convolution operations followed by deformable convolutions I'm using here. So deformable convolutions, what these are performing, I will be telling you in the later slides. So through this, I'm going for downsampling operations, and further, once you get the downsampling, let's say here one by one downsampling applied. Let's say it is 128 by 128 size. Let's say I will be getting here 64 by 64, and another downsampling is there 32 by 32. On 32 by 32, again I am applying inverse process, reverse process. It looks like encoder decoder architecture. Inverse process it is coming, and I will be getting the aligned features. These are all aligned features I am getting at last using even transformer block and even transformer backbone you have used. In this we have used a transformer backbone. So transformer block also I will be explaining in the next slide. So here key components, even I have explained that attention guided deformable alignment module is, and multi-kernel guided attention module is there, and aligned feature enriched module which is constructed from the transformer backbone. So here what is called deformable convolutions. So I need to give a example for that. Let's say what is called convolution. Let's say this is an input image, and I'm having a filter of 3 by 3. I'm having a filter of 3 by 3. So this 3 by 3 filter is taking, and on that 3 by 3, I'm applying a convolution operation which is called a dot product, and it is coming single. And again, like that, it is applying for all pixels here. And then again, you are be getting the same, one more filter will be applied here, and you are getting this. So what's happening here? It is performing this operation at equal distances. So if here this object is smaller size, maybe 3 by 3 is fine. But when an object is bit bigger here, so that time what happens? You need a bigger filter so that it can able to cover the entire object, bigger object also. So that, but in traditional convolution algorithm, which is applicable for linear time invariant systems, linear time invariant system means it is applicable for linear systems and time invariant systems. It is performing for specific distance only. It is a fixed distance, data will be collected, and based on that it is applying dot product, and it is computing the resultant information, resultant response, and it is carried forward to the next layer. But useful information case, as I am showing here, it needs to be collected for entire object. That is not happening. So but deformable convolution, what it is happening? So it is collecting the useful locations, and based on those locations it is collecting the response. It is generating the response, and it is forwarding to further level. See here, it is collecting this 3 by 3, and then further again 3 by 3. It is going further and further. 1 minute, I think some small issues there. Okay, guys. So here if I see here in convolution case, it is taking equal distance, because of that it is not able to cover the entire object. But here if you see one by one, it is coming, this it is able to cover this object with the two layers itself, and it is we are able to detect this region here. So same manner here also for 3 by 3, initially 3 by 3 means it is not exactly the fixed location. It can draw any location based on the important region or important content here. So here it is drawing this region, and from this it is a reference pixel, and it may be drawing all these locations. So and you are getting a single point here. It's like it will be changing the locations based on the content present, based on the how content distributed in the image, and based on that it is getting the responses. So we call it as deformable. Deformable means it can change the direction, or it can change the locations, and based on that it is it is generating the response. It is it is more prominent one, and it is performing far better results when compared to the simple convolutions. So that's why we use here deformable convolution in place of simple convolution. Again, if I give example, this is the one for simple convolution. But if I see here in deformable case, this one is moving this direction, this is moving like this is moving like this, and so on. So which means here it is going not even randomly, it is going based on the content present in the data, in the image. Based on the content, it is collecting the locations, and based on that it is means these locations are also a trainable locations. Deformable convolution, even in deep learning convolution layer, it is a learnable layer. Similar, deformable convolution is also a learnable layer, but these locations will be learned or generated by at the time of data understanding or data is a response case. It is not a fixed means for this kind of data, these are the deformable locations. Even it can pick the location based on the data. So we can say it is dynamically changing the location, so that we are able to get the better response based on the means if object size is getting changed, still it can able to handle for some extent. That is the advantage. And then even so, if you see this is a dilated convolutions. Dilated convolution means if instead of taking one distance, it is taking distance of 2 from the reference pixel and collecting the 8 neighbors, and it is collecting the convolution response. And similarly, this is different types of symbols you can collect, but it is not following any kind of pattern. It follows the pattern based on the content present in the image. So now let me explain how it works. Let's say I'm giving input feature map or maybe input image. So on that it is taking, let's say this is the reference pixel, and it is collecting the convolution. So you got the convolution response, and from that it is taking the kind of offsets. Offset means from which direction if I move, from which direction if I move, it is giving the more useful information from the image. Means it is kind of energy calculation, and where it is having extracting more energy. Based on that, I will decide that you go from this location to this much distance, so that draw the value to generate to get the response. So that we call it as the offsets. Offset, what it gives from this location for this 3 by 3 grid, how to move. So from this you move from this much distance this way. It will move from this way. It will move from this way, and here it will move this way. Like the different directions it will give, and the distance also can be decided. Means these are all called offsets. So that resultant data collect means offset will be utilized, and from there we are pulling the content for dot product calculation. From there you are getting the resultant response. That is called deformable convolution. Means shape is not fixed. Shape is getting deformed. Means different shapes will be formed based on the content. That's why we call it as a deformable convolution. So now coming to the with deformable convolution, one type of concept we have learned, and here attention mechanism. Attention mechanism means in initially deep learning is developed using convolution, pooling, and activation functions. and batch normalization or instant normalization, like with different types of layers. It has been it developed the we developed the deep learning algorithms. But nowadays people are using attention mechanism. So how this attention mechanism came into the picture, let me explain. Like general attention case. So generalized attention means it's a manual attention case. Let's say if I am giving an image, so it's let's say segmentation task, or maybe here I have given a task of in painting. Like if I am taking this is unwanted, means wherever data corrupted, these are white regions are all data corrupted. I need to in paint, means I need to generate the data for this to fill the entire image. So this is an output. So once we are getting the output while training, I need to give a direction to my network deep learning algorithm. So you need to generate, like I am giving this corrupted image, at the same time mask where I need to generate the information. So I need to give a clue for this with, you can say, non-blind image in painting, we call it as. So here we are not we are generating the locations where we need to restore the information or in paint the information. So when we are providing this a ground truth, means even this mask, we are going for we are using a deep learning algorithm, and using this deep learning algorithm we are generating the output. Once we generate this output, we need to check how good it is. So for checking, even while training also, we need to fix some kind of target. So it is called as supervised learning. In supervised learning, we need to give target data, which is called ground truth. So this ground, once we give ground truth, this entire model, whatever deep learning model we are developing, that deep learning model should work out for that kind of data generation only, which is nothing but I am giving certain attention, certain kind of directions to my algorithm, saying that estimate the information where data is got corrupted. That clue I am giving, so that my algorithm can learn. So this is, we call it as manual attention. Just I interpreted like that. So manual attention I given, it means you have to generate the information for this information, for these corrupted locations. But even blind image in painting or blind image restoration case, so we don't have any information about the location where data got corrupted. Still you should able to restore it. Like any restoration algorithm, if you consider, maybe denoising algorithm, or maybe dehazing, or de-raining, de-snowing, or any kind of restoration algorithm, you don't know where it got disturbed the image. Let's say this is an image, and then maybe if it is a blurred, or maybe even deblurring is also kind of thing. So if I'm having this total region is having full information, so there is no blurred content, but here this portion is got blurred. So I need to give more attention to this region to restore the means where lost in where information got lost. And this region is not necessary to keep much attention to restore the information. So from there only attention mechanism came. So this we call self-attention needs to be developed here. So network itself should develop the attention where I need to improve the quality, where I need to where I not necessary to consider improvement. So that we call as a self-attention mechanism where people started using here. So self-attention mechanism actually performs like if you are giving a feature map. On these feature maps, we generally go for either channel-wise squeezing, or maybe spatially squeezing. Like 100 by 100 image becomes means feature map becomes single value by either maybe applying average pooling or maybe max pooling. And based on that, I will be deciding, means I will be getting a single value, and from that single value, I will be means that single is a attention for that particular channel. And similarly, I can go for if I am having a number of channels. If I am having a C number of channels here, So which is nothing but C number of feature maps. If I apply average pooling or max pooling in axis wise, like channel wise, so I will be getting like if it is 100 by 100 image, I will be getting again again I will be getting 100 by 100 size feature map, but here 100 by 100 by C number of channels are there, but here 1 is there. I am getting, this is a attention content I am getting, means I am getting useful information where more energy is there, that will be highlighted more, means large value will be coming in the averaging or maybe max calculation. Either max pooling or average pooling can be done in the channel wise. So based on that, I will be getting 100 by 100. So from this, if these values are between minus infinite to plus infinite range. Whatever channel information, channel averaging or channel max pooling calculated, this will be a very large value. Infinite means I'm saying it may be negative large value to a positive large value. It can be any value in between these two. So this is a problem. I cannot able to get which is more useful information. Positive one is a more useful information, but how I can feed or how can I multiply with the my feature map so that I can able to give more importance to that region, and let's say where negative infinite size or negative large values are there, means negative large means which is very small value. So that should be given very less importance. But how to get it? So for that, people started using two types of activations. That is, one is a sigmoid activation, which converts minus infinite to plus infinite duration, becomes 0 to 1 duration. So which means minus infinite will be mapped to 0 and plus infinite will be mapped to plus infinite map to plus 1. It is not minus 1. I am just telling between 0 to 1 range. So it will be plus 1. So that way you can able to convert that into 0 to 1. And if I multiply this content 0 to 1 content with my actual feature map, so wherever 1 is there, it will be giving full importance. Wherever 0 is there, just simply ignored. And in between, let's say if wherever half weightage has given, it is given the half of the information for that, means half weightage. Like that, you can generate the resultant response where it is highlighted the more useful information or where it is more attention. Let's say if you talk about this image here, I should get the image like this. So this portion should be, this portion all should be 1, because it is, I am saying, sorry, it is opposite direction, where this is it is, there is no blurriness in this. So it means these are all less important. No need to give much importance to restore further. But here it should give more importance where we need to restore the information. Means that is the location you need to concentrate more to restore the data. So that is called self-attention mechanism. But in the self-attention mechanism further extended to a non-local attention, because self-attention mechanism is a local, it's a kind of local information or neighborhood information is collected in very local manner. Because if I go channel average pooling or max pooling, so that is collecting without considering any neighborhood information. Simply it is collecting at the channel level. So which is you can say local information. Similarly, for each channel, if I get the single value, so it is like 100 by 100 size matrix is with me. On that, I'm simply collecting the either max pooling or average pooling. I will be getting single value. So ultimately, if I apply spatially pooling, so that I will be getting 1 by C. So this is the size I will be I will be getting. So with this, with this kind of attention, it is not able to give concentrate more on to the neighborhood information. That is the reason people started using non-local attention mechanism. Let me take out this. Okay, so what is called non-local um, attention mechanism, which is actually kind of correlation it collects. Let's see if I am having an image. Let's say, so this is an image. So what it if we collect, let's say, this pixel correlated with all pixels of this remaining image, in this image all remaining pixels, if I get some correlation, so that I'm able to understand how this data got distributed in this image. So this is the actual motivation kind of thing, means kind of motivation happened in non-local attention. It is works like a correlation, one pixel with other, or one row with all other rows. Similarly, like that, it is collecting. Let's see if I am giving image size of h by 1024. So what we will do here? So even t is nothing but number of batch size here. Let's say if I apply 1 by 1 filter with 1 by 1 filter with 52 channels, I will be, even I'm just reshaping this to THW. I'm reshaping this to THW after 1 by 1 filter here, which is nothing but T by H by W by 512 becomes THW by 512, which is nothing but, if I am taking let's say 10 channels, means 10 batch size, and then H is height, maybe 100 by 100 image, and number of channels are 1024. So it is like this. So here, if I apply 1 by 1, I will be getting this becomes 512. I just reduce the dimension, nothing else I did in this case. I'm sorry. So on that, I am reshaping this all THW becomes one-sided. It's like a 2D matrix. And similarly, I am performing here. So here A is there. And let's say here A transpose is there, which is A is nothing but THW by 512. Which here 512 by THW. A into A transpose, if I get, I will be getting like THW by THW. And then I'm applying softmax layer. Even I said that here, instead of going for one is a sigmoid layer, another one is a softmax layer. If you use softmax layer, means it is going for probability. It is collects the probability by like a kind of concept utilizing Bayes theorem, or maybe kind of probability estimation. What it does, even if I'm having image like this with a different number of channels, it collects the, instead of average calculation, so it collects the probability of the all directions or in that direction, and whichever the highest probability is coming, which is the largest value, means probability generally having between 0 to 1. So softmax output is a kind of between 0 to 1 you will get. If 1 means probability equal to 1, which means more useful, important information, that location is more useful. You need to collect the 100% information from there. Like that, you have to work out. Okay. So once I apply this, you are getting THW by THW. And then again here I am having one more convolution. It is with THW by 512. So if I multiply again with this, I will be getting again same size of THW by 512. On that, if I apply reshaping back, I will be getting T by H by W by 512. So what ultimately happened here, all rows, columns, and batch, everything will be single row or single column. And then again, other one is if it is a column, other one is a row, and both will be multiplied in the matrix multiplication. You are getting the bigger size matrix. It's a kind of correlation it is performing here. So when correlation is there, it can able to get the long range dependencies. There is a long relation between one pixel with the neighborhood pixels. So this is there here. So that is the reason it able to perform better. But there is a big problem in this. Huge problem is there. means huge data utilization or data processing is required in this. What is that? Let me explain in simplest manner. Let's say here image size is 100 by 100, and then you are having t equal to 10 here. So what about this here? This is 10K into 10, which is 100K, which is nothing but here 1 lakh. This region is 1 lakh size. So which is nothing but THW is 1 lakh, means 100K divided by 100K. Okay. So you are getting a matrix size of 100K by 100K, which is 1 lakh by 1 lakh. Can you process this much image size using deep learning algorithms? It is not possible. So that is the reason people use, when we go for non-local attention, people divide the image into sub-blocks, and maybe 10 by 10 blocks or maybe 15 by 15 blocks, and then they are processing them. Even though 10 by 10, if you consider 10 into 10 by 10, which is you are getting a 1000 by 1000 matrix. 1000 by 1000 matrix also a even 10 by 10 sub-block, it is collect 1000 by 1000, which is a larger size, and it is bit difficult to process. So that is the main drawback at non-local attention. So, but here if I go for multi-head attention, further I have to go for same thing in with multiple heads, with multiple kernels or multiple sizes, multiple filters I need to do. So that is a drawback here. So to address this, people develop, why should I multiply THW by THW? If I multiply with instead of getting this THW, if I multiply, let's say THW by 512 is multiplied with 512 by THW here. If it is A and A transpose, if I multiply A into A transpose, I am getting this much huge size. But if I multiply with A transpose into A, what I will get? I will be getting 512 by 512 size, which is nothing but 512 by THW multiplied with the THW by 512. So again, multiplication is possible here. Your resultant size is 512 by 512, whatever the image size. Even you are taking 512 by 512 image for processing, ultimately you are getting there again 512 by 512. Even 1K by 1K image, you will get again 512 by 512 only. And after that, softmax is there. And on that softmax, again 512 by 512, we multiply with THW by 512. You are getting the means your TH. So this one you will be getting again THW by 512 only. So after that, again reshape back to the rows and columns, and you will be getting. So that is called here transpose convolution, transpose block. It proposed. So it got proposed in Rishormer based haze removal problem. So there it has developed, and because of that, computational complexity has reduced drastically. So the same thing you are performing with multiple heads or multiple kinds of filters. You are we call it as a multi-head attention. So this is up to existing literature, but here deformable multi-head attention we have developed here. So we have utilized the concept of multi-head attention, which is came from non-local attention. Non-local attention came from the self-attention. So this way. So, but again we are adding multi-head attention plus deformable based convolutions. So here these are all the convolutions. I will use deformable convolutions in place of simple convolution, which is called deformable multi-head attention only. So like that we have implemented, because this deformable is collecting the various locations in for feature response calculation case in appropriate manner. That we already discussed. Okay. So here it is a deformable one, means I will wherever one-dimensional convolutions one by one I will perform. After that I am performing 3 by 3 deformable convolutions. so that I'm able to get the size of means like various different locations it can able to collect. Because of that, I'm able to get the better attention mechanism I'm able to develop. So even transposed attention, I have already mentioned that what is called transposed attention. So it is actually performed for the to reduce the dimension reduction purpose. So instead of multiplying THW by 512 with the 512 by THW, we will multiply other direction so that it is decreasing the computational complexity. So this is actually the even this is a multi-attention block or maybe transformer block we have developed here, and then it is for by combining the reference and current frame, and here it is only current frame. Both are connected and future fused burst features are done here. We have feature fusion happened here. So transparent attention feature merging module is utilized the uh, whatever the response came from the aligned features, and those features are utilizing here, and then feature merging is happened. So once feature merging is done, as I said, third module is the upsampler module. In traditional algorithms, people use that only either upsample by 2 or upsample by 4 or upsample by 8 directly. But we developed upsampling like it is as it is size we are using. One is upsample by 2, another one is upsample 2 times, which is nothing upsample by 4, and here upsampling by 8. So those are all concatenated and appropriately again performed the it's a bilinear interval or bicubic base upsampling is performed. And here this one no need to upsample, this needs to upsample by 2, so this needs upsample by 4, this needs upsample by 8, so that I can able to get the image size of 8x. 8x resolution I'm able to generate here. So like that we perform the upsampling with the end sampling method. Means we are not utilizing single upsampling method. We have used the group of upsampling methods like as it is upsampling by 2, upsampling by 4, upsampling by 8. These three different types of combinations are considered, and these combinations are being utilized for the upsampling of overall resultant size of 8, resolution of upsampling 8. So resolution transfer feature, this is upsampling by, as I mentioned, this is also a contribution done our side. So coming to the results analysis here. So in results analysis, now we have compared with other existing methods for burst super resolution. Burst super resolution class, there are existing real world data sets are available. So on the training data set, we have done the training, and then there is a testing data set. On the testing data set, we have done the testing. So we have compared our method with all other existing methods in terms of PSN and SSAM. So here we are able to perform far better results as compared to all other existing methods. So if you see, this is the raw frame, which if you see directly like this, but if you apply burst super resolution with existing method, these are all the existing methods, and this is the other methods. Our method, if you see, we are able to restore the better data as compared, means we are able to upscale the image without means by extracting or by generating more information. Similarly, this is a burst SR data set is considered super resolution data set for 4x application. So if this is the image, and if you, this image, if you see in the raw fashion, this is the one HR image after downsampling base frame, and then these are all the upsampled by our means existing method, and so this is existing method up to this point. This is our method, and this is a ground truth. From this you can see our method is able to perform better results as compared to other existing methods. And other one is like apart from the super resolution, we also tested our algorithm for trained and tested on denoising, burst denoising. So here again we have compared our method with other existing methods of 4 benchmark methods, which are published in CVPR, previous CVPR and IEEE transactions. So here these are all the qualitative results. Just 1 minute. I'm in lecture. What happened? yes, 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 मैं दे दूंगा आज नाइट और कल सुबह दे दूंगा. Okay, so here if I take this is a raw noisy image, if I am collecting this image and even this portion, if I am taking this portion for the restoration, so these are all the existing methods and this is our method, this is a ground truth. So still means our method is improving better, far better as compared to existing, but still it may be required to go further for the up to the means closer to the ground truth. See here, so but these noise levels are too high. Still we are able to restore the content for betterment. So again, these are all the quantitative results for low light image enhancement. So low light image enhancement, if you see here, you are not able to see anything here. So if I go for the transformer block based attention mechanism, so this is very much important region we need to restore. And this is already having some kind of information you need to improve further. Like that, this is our results, and these are the ground truth. These are the ground truths, and these are the results of existing methods. So we also did ablation study with ablation study means like with various combinations, like we have developed 3 different types of mechanisms. One is multi-scale alignment mechanism, fusion, and another one is a fusion mechanism, multi-scale feature fusion mechanism, and third one is like a upsampler. So for alignment, feature fusion and upsampler case, we have done the ablation by keeping like one at a time or maybe two together, like with the different combinations we have considered. Based on that, we have performed, and then this is the combination with all proposed method. So there we are able to perform far better results, means better results as compared to other existing methods. This is called ablation study. So even in ablation study, we want to show some visual results, how alignment is performing. So like before alignment, these are the frames, and after alignment, these are the frames. You see here, better way you can see here. So here, this one, so but it is restored back to the original of reference frame. So same manner it is performed for other cases also. So now coming to the conclusion, here we have developed an end-to-end multi-frame. End-to-end means here we have proposed 3 modules. The 3 modules when novel contributions are done on 3 different modules, but 3 different modules are trained in in end-to-end fashion. So for burst, super resolution, and restoration purpose, and multi-scale burst feature alignment is proposed, and similarly transport attention feature merging mechanism is proposed, which is nothing but here merging the more useful information attention mechanism. So another one is resolution of transformer feature upsampler, means where upsampling by 2, upsampling by 4, or upsampling by 8 we are performing here. So finally, we are able to achieve the far better results as compared to other existing methods in terms of super resolution, denoising, and low light enhancement. Okay, so this is the one. So with this, I'm stopping my content. I hope actually this is you can say latest technology, and this is got launched. Earlier it was there in iPhone, but iPhone that time it did not consider for the processing. It is just a live photograph. It is just collecting a video, small video. If you see, it is just video playing was there. If you apply long press on that photograph, it gives you video. So otherwise, in previously it performs video, it displays video only. But here boosting image means like upsampled image will be displayed here. Guys, if you are having iPhone, please check it now. Even you can check now and tell me. So it is very much essential. Where main requirements for this development is that we should able to deploy it in the mobile phone. Mobile phone means it doesn't have very high-end GPUs in mobile phone. It is having NPUs, neural processing units are available with a very less number of very less memory. So you should able to perform. You should able to develop a models very lightweight, so that you can able to deploy them in the mobile phone for further means processing point of view. So now I'm stopping at this point. If you are having any questions, I want to take up them. Any questions, guys?
Participants, if you have any question, you may please ask.
Yeah, question is that like does it work like inbuilt system of phone camera? What exactly meaning? Like our algorithm? Yes, our algorithm is even my iPhone. They are not using, I think, deep learning. I don't know what exactly inside algorithm, because it is not known to the users. Mostly very lightweight or traditional algorithms kind of alignment is performed, and based on that only they are doing. But if you are able to deploy deep learning models, so definitely it will be performing better than the iPhone current performance. So, okay. Your question, I understand whether it is performing at a phone level, means like camera level, or in phone level. It is performing at, means camera is just collecting. We are not doing anything. This operation at camera level, we are performing at OS level, or maybe like software level. Any other questions?
So, if there are no questions, then we would like to thank Dr. Murala, because we know he is a